Well, hi, I'm Gary, ham radio operator, call sign Whiskey 4 Echo Echo Yankee. And you have stumbled into a ham radio class, a beginning ham radio class, that is. We have a group of students in our Zoom classroom and also some folks watching us on YouTube as well. And this is recorded also on YouTube, so if you stumbled across the recording, welcome. Have you ever thought about getting your ham radio license? It's a lot of fun, and it's a great group of people. And our class here can help you do that. And what seems like an overwhelming subject with new words and concepts and whatnot, hopefully will make just simple enough, just understandable enough so that you can pass an amateur radio test, because that's how you get your ham radio license, by taking a 35-question multiple choice test. And we use this book. I always love to show it. It's the American Radio Relay League. Whoop, there we go, that way. The license manual for the technician class. Technician class is the beginning license. This is the 5th edition book. This is the one that you want to get. And we go chapter by chapter in the book. And tonight is chapter 3. We're going to be talking about electricity, components, and circuits. And we have maximum 2 hours. We've limited the class to run from 6:30 in the evening till 8:30 in the evening on Wednesday nights live, if you're watching us on YouTube. To try to do electronics in this short amount of time is impossible. So we'll get started. We're going to give you the highlights, but remember, what we do is we're focusing in on the amateur radio licensing exam to make sure that we cover all of the topics there. So Bruce, if you'd go over to the laptop, please. And so here we are at section 3.1, electricity, or introduction to electronics. Well, no, not really. There are a lot of videos on YouTube dealing with the electronics, and if it interests you, it's a fascinating not only hobby but career. There are classes at community college in various locations. There's a lot to learn about, but let's go right back to the very basics of an insulator versus a conductor of electricity. So I'll ask you right now, you can go ahead and unmute. So what are some good insulators to the flow of electrons?
Air, glass.
Okay,
ceramics,
air, glass, ceramics, plastic. Okay, perfect, excellent. And what are some good conductors?
Silver, copper,
Gold.
Yep. The metals, yes, silver, copper, gold, all excellent. So insulators can be made specifically for that purpose, and the fluting that you see here on these insulators has a purpose. It adds high voltage resistance, so higher voltages can be insulated because of the way they're mechanically built. But this is probably a ceramic or a plastic material. This is an insulator. And then conductors, the wires. I was in Lowe's today buying actually some copper grounding wire. And so copper, aluminum, and the other metals. So conductors and insulators. Why does a conductor conduct? Well, because it has free electrons in the outer valence band of its atoms. And we're not going to go in depth on this at all. We do go more in depth on this in the general class when we start talking about semiconductors. But there's electrons on the outer ring that have a negative charge, and here you can see on the diagram they're moving the charge from the left to the right on the screen. So the movement of an electrical charge through a conductor is current flow, and that's what electricity is all about. So here is a schematic diagram, not so complicated. Let me turn on my laser pointer so that I can... There we go. Okay, so I can point some stuff out. So this is a schematic symbol. You'll see it in use for a battery, with the positive side of the battery up here. And electrons flow from the negative side of a battery through a load. In this case, is a light bulb. current continues to flow, and then it's stopped because this switch, this is a single pole, single throw switch, the simplest kind of switch. And when it closes, then electrons are allowed to flow back to the positive side of the battery. So this is electrical current flowing through a circuit. And if you had a chance to read chapter 3, some of this is going to be review for you, but some key concepts. Voltage is the pressure behind moving current through a circuit. We use the symbol E because it comes from the French, and a lot of science is European based, and so the French scientists came up with electromotive force, so E is used as a symbol for voltage. We also use V on schematics to indicate voltage as well. Current is the flow of those electrons or flow of charges. We use the symbol I, again from the French, intensity, and measured in amperes. So voltage is measured in volts. Current is measured in amps. Okay, amperes. Did you hear me say that? That was an old electronics instructor of mine, Mr. Zielinski, who always used to say amperes. There's no H in there, but he always used to put that H there, so it makes it sound like an F. So you'll hear me say that. This just because that's the way I learned it. Amperes, amps. Resistance is the opposition to current flow, and it's measured in a unit we call ohms. Power, that's the amount of work a device or a load is doing or utilizing from the power grid, for example. Its symbol is W, stands for watts. Power is measured in watts. And circuit is any path through which a current can flow. So that was a lot of words describing stuff, but sometimes a picture is helpful. And I have to thank my colleague Dave Ivey, who found this one on the internet. Here we have the pressure, Mr. Volt, who is trying to push the current, the amps, through the circuit. And resistance, the ohms, is inhibiting the flow of current. So here we have volts, amps, and ohms all in one picture. And you'll have a copy of this handout. You can review this tomorrow if you want when I send out the email with the links. The link is also in the description box on YouTube, by the way. So here's a review again. E, I, and R. Notice the symbols over here. Voltage, current, resistance, volts, amps, and ohms. Their role in the circuits, and some other background. Ohms, we use the Greek letter omega as the indicator for ohms. So we looked at a battery earlier. That's direct current. Batteries are direct current, meaning that their polarity doesn't change. As long as it's oriented in the same direction and you've hooked up the wires, in this case the voltage is going to go positive, and over time it's always going to stay at that same amplitude, whether it be like 12 volts or 9 volts. That's its amplitude on the vertical scale in volts over time. Whereas alternating current, the house current that we have in the United States, 120 volts AC at 60 cycles per second or 60 hertz, it alternates, starting at a 0 volt point, going negative, back up to 0, positive, back to 0, and then completing the cycles again. 60 complete cycles in 1 second, 60 hertz. So this is DC, where it's always on one side of 0. Either it could be positive polarity like we see here, or it could be negative polarity if it were to be down here. That's a DC. Its polarity is doesn't cross the 0 line, let's say. Whereas alternating current goes from 0 negative, 0 positive, 0 negative. That's alternating current. Okay, got a trick question for you. Is this AC or DC? Anyone want?
Pulsating DC.
It is pulsating DC. Notice it never goes opposite in polarity. It never goes negative. It goes down to 0, but then it goes back up again. So this is a form of DC, and it's what you might see in power supplies before filtering is done in an electronic power supply. So that was a trick question. Good job. Schematically, we saw that the battery, the symbol that we looked at before, here's a resistor instead of the lamp that we had before. This is a resistor symbol acting as a load, and current is flowing in this circuit through this resistor and back. Alternating current, much the same. This is the symbol for an AC generator or an AC source. But in this case, the current goes out to the load and then reverses direction, comes back through the load, then reverses, goes back through the load again, and back and forth 60 times a second in an AC circuit. Why do we have AC? Why do we have DC? It goes back to Edison and Tesla. Come back to me for a second if you would. Thanks, Bruce. Edison was a real strong proponent of DC. He thought DC was the way to go to power homes, to power work, or whatever. Tesla, however, the mad scientist Nikolai, not of car fame, but of electronics fame, he believed that alternating current had great advantages in that you could use generators to generate the power. The generators could be turned from water sources or other wind or things like that. And AC can go through transformers. We'll talk about those a little later. And can be ramped up in voltage or brought down in voltage through transformers and transmitted over long distances. Remember, DC stays at a certain voltage all the time, but AC can be taken up to a very high voltage and brought back down to a low voltage. And the high voltage long distance transmission lines, you know, you've seen those big towers? That's why. They're running at multiple kilovolts up there in the sky, and then they're transformed back down to our normal voltages that we use in our home, and there's very low loss up on the wires in the sky. So in the end, Tesla got together with Westinghouse, and AC won the day. So that's why we have AC in the United States, except in your car. In your car, you're going to have a DC battery, whether it's a gasoline engine or one of the new EVs. Here's lead-acid 12-volt batteries that you might find in all the cars. And in these, energy is stored in the batteries chemically and then is released to start the engine or to power devices in the vehicle, for example. So,
question.
Yes, please.
When is it advantageous to have DC rather than AC?
You can take me off the picture-in-picture there, Bruce. Sorry. So DC, what is it? Well, batteries are all DC. There's no such thing as an AC battery. So for portability, you're going to have a device that's going to be DC powered. DC, as I mentioned, is always up at one voltage level, so it's always able to deliver maximum power at all times. You saw that AC fluctuates, so there's a diminution of the power, the effective work that can be done because of the AC. That can be worked around for different methods. So it's a good question. I'm not sure I really answered it, but
yeah, you answered it.
I'm glad you're thinking about it. So
we also, the answer I'm looking at.
Yeah.
In our machinery, we use DC to run a motor one way, and then we reverse the DC current to make the motor go backwards.
Correct. You can do that with DC motors, absolutely. Yeah, you're thinking. I like it. All right, so with electronics and electricity, the single most important relationship has come to be known as Ohm's law. And Ohm's law is named after this guy. George Simon Ohm, we would say in America, or Georg Simon Ohm, who was a German physicist, and he postulated the relationship between voltage, current, and resistance. And if you look at the picture there on the upper right-hand corner, that's a cemetery. As some of you might know, I worked for the Voice of America for about 20 years as a Foreign Service Officer, and I was posted to Germany in 1990 through 1993. And I happened to be in Munich, that's where my posting was, and I had to go to a meeting, so I had to walk to it through town, and the quickest way to get there was through this cemetery. And as I'm walking through the cemetery, I tripped on the corner of a grave, and I looked down. It was George Simon Ohm's grave. So that's a complete side note, has nothing to do with the class, but I've been there. I salute you, sir. But Ohm's law is very much like we looked last week at the relationship between frequency and wavelength. And if you remember, we said that we had the speed of light up on top, 300 million meters per second, or if we could just abbreviate it to 300, and we had the frequency in megahertz and wavelength in meters. And so we know that if we know two of these, we can find the third. Well, the same thing applies, the same relationship applies with Ohm's law. EIR, and you can draw this as a pyramid as you see it here, or in a circle. Sometimes people do it that way. E for voltage is on top, current and resistance are underneath. And what this pyramid is saying is three mathematical formulas, three mathematical relationships. If you know the voltage in a circuit and you know the current in the circuit, you can figure the resistance by taking the volts divided by the amps, and you'll get an answer in ohms. You use the pyramid and you block out what it is that you're trying to find, and E is over I. That's what this is all about. E is over I. Similarly, if we're trying to find current, well, we can put our thumb over the I, for example, or block it out here. It's E over R, or E divided by R. So volts divided by ohms will give us the amount of current flowing in the circuit in amps. And lastly, voltage, if that's what we're trying to find, is current times resistance. This is a formula that technicians use every day of the week if they're involved in electronic circuits or whatnot. If they can measure the voltage across a resistor, and they can then calculate the current. So it's a fundamental thing. And well, Gary, but I want to be a ham radio operator. I want to, just talk on the radio. Why do I need to know this? Well, because amateur radio operators have the capability of building and modifying their own equipment and repairing it and putting it back on the air again. So the FCC wants hams to have at least a basic understanding of electricity and electronics. So that's why Ohm's law is on the test. And so we'll talk about some problems coming up here. So that was Ohm's law. Then there's Watt's law, dealing with power. Power in watts, current in amps, voltages in volts. Ear pie. Okay, that's kind of sounds gross, but ear pie, these are the formulas to remember, or the pyramids, the relationships to remember. And if you remember these, then you can derive the formulas that you might need to calculate. Now, I don't want to scare you, but from these two pyramids with these relationships, you can derive all of these formulas. So if you know power and you know voltage, well, you can calculate the current. You don't need to know these. You do need to know these. So restrict yourself to this at this point in time. But I want you to know that these are the basis then for other calculations, so you can actually figure out things that are going on in a circuit in reality. We looked earlier at a circuit with the battery and the lamp and the switch. Well, here's another one. We just have multiple lamps in this case. Here's our power source. Electrons flow from negative through the bulb, up through another bulb, up through another bulb, through a switch, and back through the battery. This is a series circuit. The lamps here are in series with one another. The current flows through one, then it flows through the other, then it flows through the other, through the switch, and back. This is the Christmas tree dilemma, the Christmas tree light dilemma. You know, when you got one of them burned out, it's because they're in series. And when one burns out, it becomes an open circuit, an open switch, and current cannot flow. So this is a series circuit. This is a pictorial of a series circuit. And here's a schematic diagram of the equivalent minus the switch. Here's our battery again. And instead of lamps, we have resistors. This is the schematic symbol for a resistor. Again, they're all in series, so the current flows through each of them in turn and then back to the voltage source. So series circuits. Of course, there's going to be an opposite. The opposite of series circuits are parallel circuits. Here we have a voltage source in the pictorial, and it's connected up to a lamp here. But this other lamp is also connected directly back to the power source, and this third lamp is connected back to the power source as well. In this case, if one of the lamps burns out, the other two will continue to illuminate. So this is a parallel circuit. And schematically, it would be drawn something like this with the battery, and in this case, we're using resistors to substitute for the lamps there. This is a high-level concept. You can take it into actually a class, Kirchhoff's laws, but battery sources here, you have current flowing through in series with R1 and R2. The current through series components are the same. So the current that flows through R1 and through R2 will be the same. The current, however, in parallel circuits divides. And if these were equal value resistors, then you would have half of the current flowing through this resistor and half of the current flowing through that resistor. So the difference between series and parallel and current division at the junctions. Used to be a test question, not so much anymore. And also voltage across resistors, if they're connected in series, the voltage divides. So if you've got 10 volts coming in, let's say here, and we have equal resistors, let's say 1,000 ohms and 1,000 ohms, then you will measure 5 volts from here to here, because the voltage divides across this resistor and across this resistor if they're equal values in equal ways. Or you can, if you change the ratio, you can change. This is known as a voltage divider. And it's very handy, especially in, not so much in power circuits, but in audio circuits. If you need to take a line level signal and bring it down to a microphone level signal, well, a voltage divider circuit like this can do that very nicely. The voltage across parallel connected resistors is the same as the source. Remember, we said in the series, it's going to divide. The voltage divides up between them. But in a parallel circuit, the voltage will remain the same across the resistors. If it's 12 volts here, it'll be 12 volts across this resistor, 12 volts across this resistor, and 12 volts across this resistor. The current coming from the source is going to divide up, however, in a parallel circuit. All right, some terms there, series circuit and parallel circuit. Here's one we've all heard of. Do we really understand it? A short circuit. A short circuit is such that if you've got a power source and it's supposed to be delivering current to this lamp, but let's say a piece of wire falls across the connections, that's a short. And what happens is it takes all of the current, because it's a very low resistance, and goes around the lamp and back to the source, and so the lamp will not light. So that's a short circuit. If you say, man, I think my device has a short, that's what we're talking about. And the opposite is an open circuit if the wire falls off. Okay, so we've got a short circuit and an open circuit. Some definitions here. And meters are always handy to have in the workshop and on equipment and whatnot. A meter is something that displays amplitude on a numbered scale. And you can have meters for voltage, you can have meters for current, you can have meters for resistance, you can have meters for power. All sorts of different things can be expressed in either an analog meter, an old style meter with a needle here, or a digital panel meter is what we're looking at here. Those are meters that are displaying the amplitudes of something, voltage in this case, on a numbered scale. When you're going to hook up one of these meters, know that a voltmeter is connected in parallel with a device under test. So right now we want to know, what is the voltage across this lamp? So we connect the voltmeter, a voltmeter, in parallel with the lamp. Ammeters, however, the things that are measuring current flow, you have to break the circuit and insert the ammeter in series with the load, in this case the lamp. And so ammeters are connected in series with a circuit. Voltmeters are connected in parallel with the device under test. And meters can be all sorts of different types. We saw the panel meters earlier. You can also have what are known as multimeters. I have one over here on the calculator cam. Bruce, you can just show it briefly. It's an analog multimeter from Radio Shack from years gone by. All right, come on back. Here on the presentation, we have an analog meter, like we have over there, and a digital voltmeter, or multimeter in this case. And the multimeters can measure voltage, they can measure current, they can measure AC, DC, and they can also measure resistance. All right, come back to me just for a sec. This is kind of controversial, but I'm going to let you in on a big secret that only seasoned hams really know. And that big secret is that everything in electronics runs on smoke. Yeah, really? Back to the presentation. Smoke. That's the big secret. You don't want your electronic circuit to smoke. And your electronic circuit could be the multimeter. So I mentioned that a multimeter can measure volts, amps, and ohms, but the thing is, and this, if you buy a multimeter and you're just starting out using it, you are in a live circuit, for example, that's powered up, and you want to measure voltage in that circuit, but you forget, let's go over to the multimeter, you forget, so there the meter is off. Here's the resistance scales. Here's some DC voltage ranges here. But if you forget, if you want to measure DC voltage, but you leave it on resistance, you know what will happen if you put your probes into the live equipment? You'll let the smoke out. You'll let the smoke out of the meter, out of the voltage divider resistors that are inside the multimeter will go poof. So that's my proof that all electronics is run on smoke. And you can see here a damaged multimeter in the presentation, Bruce. When you use the ohm meter function in a live circuit, you're going to burn up the voltage divider resistors. All right. The other thing to keep in mind is that the little Radio Shack meter that you saw over there, that's probably for home use. It's not for industrial use, for any high voltages. Come on back to me just for a second, Bruce. These are the probes that came with that meter. In fact, let's look at the calculator cam. Here's the probe. It's not very substantial. And notice it's smooth. If your hands are sweaty, they could easily slip down and your fingers could get on the metal part and you could electrocute yourself. That's no good. So you want to keep in mind that the meter is probably designed for a certain voltage range, and the probes themselves are designed for a certain voltage range. So here's another probe. This is a little better. This is an aftermarket probe. Notice it's got a ridge right here so that your hand can't slip down. It's also got a cover to keep the metal part away from your fingers, and it's just got a probe point out here, if you can see that, if it's focused. So this is better. But if you're going to measure high voltage, come on back to the camera there, Bruce, if you would. Camera, please. Thank you. This is what you want for high voltage. This is what is known as a high voltage probe. Notice it's very substantial. I'm not going to get my hands out there. Very long piece of insulation here, and then the probe tip out here. So the meter and the probes must be designed for the kind of voltage that you're going to be checking. So if you're going to be checking 1,000 volts, 10,000 volts, or whatnot, you want one of those big probes. So, or one like this, for example. Proper quality, proper device equals safety, and that's something that's always important. All right, we're going to jump the gun on something here, but brief explanation. Capacitors in a DC circuit. So a capacitor, and we'll talk about it more here in a second, is a plate or two plates of conductive material. It could be aluminum, could be copper, could be anything, that are separated by an insulator. Could be air. And these two plates, when current flows from a battery, it will start piling up electrons on one of the plates, and the absence of electrons on another plate. And so in the case of this circuit, we have a light bulb over here, we have a battery here, and if we apply the circuit to the battery, briefly current will flow through this capacitor until it charges up and can't accept any more electrons. And during the charging period, the bulb will light up. But after the capacitor is charged, the bulb will go out because it can't accept any more electrons. Well, the same kind of thing can happen in a circuit if you have your ohm meter function on your multimeter and you're doing a test in a circuit unplugged. Remember, you don't want to let the smoke out. Unplug, and you put your probe in there and you see a low resistance at first, and then it rises to a high resistance. What's happening is there's probably a capacitor in the circuit, and you're charging that capacitor. So resistance is low at first, and then it goes high. Why this question is in this section, I'm not sure, but okay, they put it there, so we'll cover it. All right, speaking of questions, go ahead and you can unmute. And we have a 3-second rule, please. Think about it for 3 seconds, and if you're answering all the questions, let somebody else have a chance to do it. Let's see what we're going to look at here. So electrical current is measured in which of the following units?
Yeah.
I heard a D. If that's what I heard, you are right. Amperes. Electrical current is measured in amps. And electrical power is measured in which of these following units? Power? Watts. So you buy well, you can't buy a 100-watt light bulb much anymore, but you used to be able to buy, or your refrigerator, when it's running, uses 200 watts or something like that. That's the amount of power that it's consuming. Power is measured in watts. And what is the name of the flow of electrons in an electric circuit?
Alpha.
No, the flow of electrons.
Oh, current.
Current, D. Yes, indeed. And what are the units of electrical resistance?
Mohs.
No. You tripped over his grave.
Ohms.
No, I tripped over his grave. Ohms. George Simon Ohm. Interestingly, Mohs is an electrical unit. It's a unit of conductivity, whereas ohms is the unit of resistance. But ohms is the answer here. And what is the electrical term for the force that causes electron flow?
Electromotive force.
Electromotive force, correct. And what's another name for that?
Voltage.
Voltage, A. Yes, indeed. These are actual questions that'll be on your test, and these are the actual answers. It's just that the answers will be in a different order, so don't memorize A, B, C, or D. That won't do you any good. But you are answering test questions right now. So why are metals generally good conductors of electricity?
B.
B is correct. They have many free electrons in their outer shell, the outer valence ring of the atoms, the metals. And which of the following is a good electrical insulator?
A.
No, A is copper is a conductor. What's a good electrical insulator? Glass. B, correct. So which of the following describes alternating current?
D.
Charlie,
No, it is Charlie. Remember we said for alternating current it has to go both positive and negative. Anything that goes between positive and 0 is pulsating DC, or anything that goes from negative to 0 would also be a pulsating DC, just of the opposite polarity. So it can't be all of these. No, it's the current that alternates between positive and negative. And which term describes the rate at which electrical energy is used?
C.
Power, measured in watts, correct. And what type of current flow is opposed by resistance? Read carefully.
Delta.
Delta,
So that's my hint when I say read carefully. Direct current is absolutely opposed by resistance. Alternating current is also opposed by resistance. Radio frequency current would be opposed by resistance. So all of these choices are correct. Okay, what formula is used to calculate electrical power in a DC circuit? Remember our pyramid? We had the ear pi. Power is equal to
A.
alpha,
I times E. Do we all understand that? Let's go over to the blackboard. I just want to write it out just to make sure. So here's our pyramid. And we want to find P. So we can put our thumb or whatever over that, and we're left with I next to E, or I times E is what we're trying to say. So P equals I times E. Did that show up very well on blue? Okay. And let's see. How much power is delivered by a voltage of 13.8 volts at a current of 10 amps?
A.
So again, this is the power is equal to voltage times current, or current times voltage. So 13.8 times 10 is 138 watts. So let me go back over to the blackboard. So we said it was 10 amps times 13.8 is going to be 138 watts. Amps times volts equals, in this case, watts. That blue didn't show up so well. Okay, good. And how much power is delivered by a voltage of 12 volts and a current of 2.5 amps? So again, we're trying to find power.
B.
And how did you get that? You're right.
12 times.
BI.
Yeah, 12 times 2.5 is going to give you 30 watts. And how much current is required to deliver 120 watts at a voltage of 12 volts DC? Oh, now we're looking for current.
E.
She says B, and she is right.
Bravo.
In this case, we're using the same pyramid. 100. Yes, exactly. 120 divided by 12, and that gives you 10. 10 amps. Good job. And what formula is used to calculate current in a circuit? So this is the ear part of our pyramid. So ear.
Bravo.
Yeah, bravo.
Yeah, I is equal to E divided by R. E over R. Correct. And what formula is used to calculate voltage in a circuit? EIR. You want to know voltage, or the electromotive force.
A.
A is correct. E equals I, amps, times R, ohms. All right. What formula is used to calculate resistance?
B.
Bravo.
Bravo is correct. Its resistance is equal to E over I, or E divided by I. And I'm going to provide you with what we call a memory dump sheet with these pyramids on it. That's something that when you walk in to take your test, you're given some scratch paper. You can put these formulas all down on the back of the scratch paper so you can remember. So when you get starting to take, well, what was that? It was ear pie? What? Nah? Okay, So what is the resistance of a circuit? So now we're looking for resistance in which a current of 3 amps flows when connected to 90 volts. R equals
E over I. Be
Yeah.
30. Bravo.
So 90 divided by 3 is 30. Yes. And what is the resistance of a circuit for which the applied voltage, so we're now looking for resistance, applied voltage is 12 volts and the current flow is 1.5 amps. So R equals
C Charlie, 8 ohms.
and how did you get that?
12 divided by 1.5.
Right, E over I, or 12 divided by 1.5 gives you 8 ohms. And what is the resistance of a circuit that draws 4 amps from a 12 volt source? R equals
A.
It is correct. 12 divided by 4 is 3. 3 ohms. And what is the current in a circuit with an applied voltage of 120 volts and a resistance of 80 ohms? So now we're looking for I. So we put our thumb over the I and we see there's E over R.
D. 1.5.
D, 1.5 is correct. 120 divided by 80 gives you 1.5.
That's using my head. No calculator.
Bravo. And what is the current through a 100 ohm resistor? Now we're looking for I. Current through a 100 ohm resistor connected across 200 volts. I equals E divided by R.
2. C.
2. C is correct. 200 divided by 100 is 2. And what is the current through a 24 ohm resistor, so now again we're looking for I, a 24 ohm resistor connected across 240 volts. I equals
E over R. So Charlie,
240 divided by 24, Charlie, 10 amps, correct. And what is the voltage, now we're looking for voltage, so E, across a 2 ohm resistor if a current of 0.5 amps flows through it? E equals
IR.
and so
1 volt.
yes, 2 times 0.5 is 1. Half of 2 is 1. 1 volt. And what is the voltage across a 10 ohm resistor? Now we're looking for voltage again. If current of 1 amp flows through it? E equals?
Bravo. 10 times 1.
10 times 1 is 10 volts. These aren't hard, it's just keeping the relationship straight. So what is the voltage, now again voltage, across a 10 ohm resistor if a current of 2 amps flows through it?
D.
You see how fast you got that? D, 20 volts, correct, you're doing it. So in which type of circuit is DC current the same through all components?
A. Series, yeah.
That's a series circuit. The current flows through one and then through another, so it's the same through each device. And in which type of circuit is the voltage the same across all components?
Bravo.
Parallel.
That's a
Bravo.
parallel circuit, yes indeed, B. And which instrument would you use to measure electric potential? Also known as
Bravo.
force. Yes, it's a voltmeter. Electromotive force, or is also known as electric potential. I didn't use that term, but yes, that's right. And how is a voltmeter connected to a component to measure applied voltage? Voltmeters
That's
are,
in parallel, right?
voltmeters are connected in parallel, correct. And when
Thanks for your
configured,
wonderful picture.
hey, good. When configured to measure current, how is a multimeter connected to a component? To measure current?
Alpha in series.
Yes, because an ammeter is kind of like a turnstile at a stadium where it's counting people going through. In this case, it's counting electrons going through our current flow. So it's in series. And which instrument is used to measure electric current?
An ammeter.
An ammeter, measuring amps, correct. And which of the following can damage a multimeter?
Charlie.
Attempting to measure voltage when you have it set for resistance, you'll let the smoke out. Don't do that. You will do it. We all do it. We've all done it. Which of the following measurements are made using a multimeter?
Charlie.
You can measure voltage and you can measure resistance with a multimeter. The others not. And what reading indicates that an ohm meter is connected across a large discharged capacitor?
Is it
Alpha.
alpha? It increases.
Yes, it starts out low and then increases with time. That's that weird question that they have here, but yep, that's right. And which of the following precautions should be taken when measuring in-circuit resistance with an ohm meter? And this is a valid troubleshooting procedure. Technicians do it all the time.
Bravo.
Yeah, ensure that the circuit's not powered or you'll let the smoke out. So which of the following precautions should be taken when measuring high voltages?
Use the right equipment.
Exactly, so that would be,
Bravo.
B, ensure that the voltmeter and leads are rated for use at the voltages to be measured. Ladies and gentlemen, you have done great. You measured, went through some of the harder topics of tonight. And what we have right now is a 5-minute intermission. So go ahead and get yourself up, stretch, get something to drink, and come back refreshed, and we'll complete Chapter 3 on the return. Thanks. are back. So I was just chatting in the break with Lee, one of the students in the Zoom classroom, and he made a great analogy, which let's do it together so we can all learn from it. Let's go back over to the chalkboard, if you would, or the blackboard. And we were talking the analogy between electrical circuits and water and plumbing. True. So, you know, you've got in your town or whatever, you've probably got a water tower. And from this tower, it's up high, so it's generating, it's got water up there under pressure. And the pressure is the same as voltage, caused by gravity from the water tower, all right? And the water is the same as the current flowing through the pipes. And if you have a flange or a restriction on the plumbing or whatever else, that's resistance. So if you want to think of an electrical circuit, it's plumbing for electrons. Just as simple as that. Okay, it gets a little more complex. But let's move on to section 3.2. We're going to talk about components and units. We've already seen this little guy. This is the schematic symbol for a resistor. And resistors are devices that are made of carbon material usually, or could be metal or other resistive elements, made in component packages like this. Or nowadays we have surface mount devices. They're so tiny you have to almost use a microscope to see them, which are also could be resistors. Resistors, the definition is opposes current flow in a DC circuit. But we answered a test question earlier, Gary, that we said it opposes DC, it opposes AC, it opposes RF. That is true. That is all true. But for purposes of the chapter, resistors oppose current in a DC circuit, and resistors are measured in ohms. And what we're looking at here are resistors with a color band system. It's a color code. And if you can read the color code, you can know what the value of the resistor is supposed to be, plus or minus whatever its tolerances are. And so, you know, inexpensive resistors have maybe a 20% tolerance. More expensive resistors, 10% tolerance. Precision resistors, 1% tolerance. But these are resistors. And here's, again, that color band. Resistors opposing DC current flow, and voltage and current through the resistor are in phase. What does that mean? Well, as voltage goes up, current through the resistor will go up at the same rate, at the same time. So as voltage goes up, current will go up. As voltage goes down, current will go down. Well, Gary, doesn't that happen in all devices? No. Stay tuned. You can have variable capacitors, resistors, variable resistors. What you might have is a volume control. They're also known as potentiometers because they change their resistance. They can be rotary, they can be all sorts of different styles, but they're measured in ohms, used for controls and volume controls, and the schematic symbols are here with a 3-terminal device or a 2-terminal device. These are variable resistors, also known as potentiometers. All right, here's our friend the capacitor. We talked about capacitors before. They're two plates of material separated by an insulator. Now the plate I'm talking about could be aluminum foil or a special kind of mylar foil. And the separator could be a plastic or could be a chemical and another plate. And it could be rolled like a jelly donut. True. And so these are some small capacitors, electrolytic capacitors, for example, are made in this way. Here's the schematic symbols for the capacitors. Here, a fixed capacitor. Here's a polarized capacitor. This means that the capacitor has to be installed one way only. If you install it the other way, if it's an electrolytic capacitor, it could explode. That's true. So that's why the plus there. And this is a variable capacitor with the arrow through it here. So capacitors are made up of two or more conductive surfaces separated by an insulator. The insulator could be air, could be plastics, could be something else. Capacitance is measured in a unit called the farad. And capacitors are generally not full farad capacitors. In fact, when I started studying electronics in high school in the 1970s, it was physically impossible to build a 1 farad capacitor. The technology did not exist. You couldn't do it. But a millifarad or 1,000th of a farad, okay, you could build that. Or a microfarad, a millionth of a farad, yes, you could build a capacitor of that value. Or a nanofarad, 10 to the minus 9, okay, yeah, we can do that. Or a picofarad, a billionth of a farad, yes, you could build those. But you could not build a 1 farad capacitor. And here's various styles of capacitors. Ceramic disc capacitors are here. Electrolytic capacitors used in power supplies like here. Mylar capacitors down here. All sorts of different types used for different purposes for audio coupling and things like that. So remember I said in the 70s you could not build a 1 farad capacitor. Today, you can go to Mouser Electronics, here's the part number, and you can order a 3,000 farad capacitor. Impossible. We are living in the future, my friend. Now, $60, it's more like a battery than it is a capacitor. But this is what it is. They're known as supercapacitors, and they are available for purchase right now. Go ahead.
What's the physical size of it?
About the size of a AA battery.
Wow.
Now notice it's only rated at 2.7 volts. But yeah, it's amazing. So these are supercapacitors. You probably won't have any need for a supercapacitor unless you have a circuit where you really want to filter power or something like that. You may have a use for a variable capacitor like this. So this has a shaft here where you'd put a knob, and it turns a portion of the capacitor called the rotor, for rotate. This rotates, and the stator stays stationary in this frame, and the plates rotate in and out, and the capacitance between all of these plates gets stronger or increases or reduces. This is a variable capacitor used in radios for tuning, for example, or test equipment and things like that. So that's a variable capacitor. Capacitors block DC current flow. Other than that brief inrush of current we talked about earlier, once they're charged, they block DC current flow. Capacitors resist AC current flow, meaning that AC will flow back and forth because its polarity is always changing, so the electrons can build up on one plate and then build up on the other plate and then back and forth and back and forth. So capacitors resist AC current flow but do allow it to pass, storing energy with those electrons on the plate in something called an electric field. You could also call it an electrostatic field, but the definition is an electric field. Capacitors store energy in an electric field. The ability to resist AC current is called capacitive reactance. It's measured, it's called X sub C, and it's measured in ohms. Now, its reactance ohms are not the same as the resistance ohms, but we still say ohms. All right? Here's our plate. Here's our electric field, which is built between the two plates as current is allowed to flow from the AC source here. Let's say it's flowing in this direction first. Electrons are building up on one of the plates. Then it alternates and goes back the other way, and electrons are then building up on the other plate, back and forth, and there is an electric field that exists here. So we say that capacitive reactance, capacitors, oppose AC current. And here's an interesting thing. voltage at the capacitor and current at the capacitor are out of phase due to the creation of the electric field. So current goes in first because it's going in, trying to build up electrons on the plate, whereas voltage takes time to build up. So we say that voltage lags current on a capacitor. This is more information than you need to know, although we do cover this in the general and the extra class. So stand by. But I want you to know really what's going on in a capacitor. What the heck is this, Gary? This looks like just a coil of wire. Well?
I have a question.
Yes, please. Come on back.
I'm a little confused between a farad. I don't understand the concept of a farad. If we're talking about capacitors as resistors, then what is a farad? Is a farad only in a DC circuit?
We're going to talk about ferrites here in just a second. Ferrites are involved with inductors. Ferrites are not involved. Yeah, ferrite materials are involved with inductors.
No, F-A-R-A-D.
Oh, farad. Okay. Yep, good. Come on back to me just for a second. So, yeah, the ability of the device to store electrons is measured in a unit called farads. Gotcha. Okay. And so you can buy a 1 farad capacitor, like I said, or now you can, or a 1 millifarad capacitor. And that capacitive device opposes AC current flow based on a formula. You're not going to like this, but okay, I'll show you the formula. You don't have to know it yet, but in answer to your question, let's go to the board. All right. So the formula for resistance, for the amount of resistance it has to an AC current flow, oh, no, I think I just maybe made my camera track. No, okay, good. X sub C, capacitive reactance, so the amount of opposition to flow, is equal to 1 over 2 pi FC. I said you wouldn't want to know this. F is the frequency in hertz. C is the capacitance in farads. So reactance comes from farads via this formula. Now we won't have to go into that at all in this class, but in the next classes, general and extra, we absolutely will. So that's where we get to reactance, capacitive reactance from farads. Good question. And I'm sorry I hadn't explained that to you. All right, here we are, inductors, which are coils of wire. And the coils can be wound around air, as you see here, or it can be wound around iron, or what I thought you said was ferrite material, which is a ceramic iron. And inductors come in all sorts of shapes and sizes. And like other circuits, we can have parallel inductors, or we can have series inductors. So is this a parallel or series arrangement?
Parallel.
This is parallel, absolutely, all right? And inductors, their ability to store energy is measured in henries. The inductive unit is Henry. So you can make a 1 Henry inductor, or you can make a millihenry inductor. So inductance, we say, is measured in henries. Inductors, because they're just coils of wire, pass DC current flow. So remember we said the capacitors blocked it, inductors pass it. Inductors resist AC current flow, storing energy in a magnetic field. So where capacitors store an electric field, inductors store in a magnetic field. They build up magnetic lines of force and then it collapses again. Those are inductors. And inductive reactance resists AC current flow, and it's a unit called X sub L, and this reactance is measured in ohms. All right, I got to do it. We did it for capacitance. I have to do it for inductance as well. And this is good. So for X sub L, inductive reactance in ohms, the formula is 2 pi, the letter pi, the number pi, F L. Frequency in hertz, L in henries. Now I want you to notice some differences here. With capacitors, it's 1 over 2 pi Fc. For inductors, it's 2 pi Fl. One is inversely proportional to the other. That has magical properties in radio, and we'll be talking about it in the future. So inductive reactance, it opposes AC current flow. Voltage and current at the inductor are out of phase with each other due to the creation of the magnetic field. In this case, the voltage leads current with an inductor. Again, this is more information than you need to know, but it's foundational for the material that comes later. And we said that you could build your coil around an iron core, for example, to increase the number of henries in the coil. You can actually then have two built around the same iron core, in this case. And we have a lot of turns here, fewer turns here. This is a transformer. Remember I mentioned Tesla earlier, and Tesla said with AC, we can use transformers to go up in voltage or we can go down in voltage. Well, that's what this is. This is a step-down transformer. I know that because there are more turns over here than there are over here. So we could have high voltage, let's say 120 volts AC coming in here, and we might have 12 volts AC coming off of the secondary of this transformer. And it's sharing the energy through the magnetic field in the transformer core. It's a specialized kind of inductor. And in a schematic, a transformer looks like this. Here's the transformer with lots of turns on this side, fewer turns on this side. So this is a step-down transformer. Notice it's got a tap at the center. So this is what is known as a center-tapped transformer. And the rest of the circuit, we have a plug to go in the wall. We have a switch, a single pole, single throw switch, the most basic. A fuse for circuit protection, and then the transformer here. This is very much like the start of a power supply that you might use for equipment to take 120 volts down to a lower voltage and then maybe rectify it, more to come, turning it into DC for units. All right. I'm just going to introduce you to this concept. You don't have to understand it, but note that impedance is the opposition to AC current flow caused by the combination of resistance and reactance. And that reactance can either be inductive reactance or capacitive reactance. And the impedance unit of measure is the ohm. Probably all hooked up a stereo system at one point or another. Used to be a big thing back in the hi-fi days. And do you have 8 ohm speakers or do you have 4 ohm speakers? So 4 ohm speakers are better than 8 ohm speakers. Well, okay. That's impedance, the impedance of the speaker. It's a combination of the DC resistance of the wire making up the voice coil in the speaker and the inductive reactance at audio frequencies of the coil. That's impedance. This happens at audio frequencies and it happens at radio frequencies as well. I mentioned the single pole, single throw, or SPST type switch, the most simple type. Well, they also have single pole double throw switches. So this is the kind of switch you might get if you have a stairs and you've got light switches at the top and the bottom. This is the one that they use for that. And they're all sorts of other complex types like the double pole double throw, for example, which is a kind of a universal type switch. But you need to know about the single pole single throw and single pole double throw. They're important. And you can control switches sometimes with other control voltages by using a relay. And here we have a single pole double throw relay with a solenoid coil here that when you apply energy through the solenoid coil, it creates a field that pulls this arm and moves the switch. So a relay is an electrically controlled switch, and they come in all sorts of different flavors, used in a lot of different sorts of electronic equipment. So in an earlier schematic, we saw the fuse as a protective device. Fuses and circuit breakers are designed to open the circuit. Remember, we saw the open circuit? And stop current flow if too much current is drawn. So if you've got a 5 amp fuse and all of a sudden it blows, well then you know at some point in time more than 5 amps was being pulled through that fuse, causing it to open up. Likewise with the circuit breakers. If a circuit breaker trips, if it's a 20 amp circuit breaker, well then you know that at some point in time more than 20 amps was being asked to be pulled through that breaker. They're protective devices trying to keep us safe, prevent fires, etc. Always want to use the proper size fuse and circuit breaker. So if you got a 5 amp fuse that blew, don't put a 20 amp fuse in there because you'll let the smoke out. I'm just saying. All right. Semiconductors are specialized kinds of materials which have free electrons in the outer ring in a certain pattern, a certain matrix. And the most basic kind of semiconductor is a diode. A diode, here's the schematic symbol up top. You see the arrow, you see it's pointing in one direction. It allows DC current to flow in only one direction. So if we were to put a positive voltage here, current would flow out to a load and back to the source. Whereas if we put the positive voltage here, it would be blocked by the diode and would not go any further. So this is the most basic kind of semiconductor device. And if you wanted to know which, an anode is the input side, for example, to the diode, and the cathode is the output side. The cathode is marked by a stripe on the physical device. And you can find big diodes for power use, and you can also find small diodes like the small germanium diode here, which is used for signal sensing and rectification. When you're passing DC current through a germanium diode, 0.2 volts DC will be left across the diode, whereas if you pass current through a silicon diode, 0.7 volts DC will be across the diode. So this is a way you can identify a diode. Is this germanium or is this silicon? Germanium have 0.2 volts, silicon have 0.7 volts. And this type of diode right here, the silicon diode, is most likely going to be used in a power circuit where you can actually take AC voltage and convert it to pulsating DC, what we saw earlier. And then if you then send that to a big capacitor, the pulsating DC is sent to a capacitor in parallel, the capacitor will smooth out those voltage fluctuations and you get pure DC. That's the basis for a power supply. And then after that smoothing out process, here's our filter capacitor, for example, we have the pulsating DC, smoothed out the voltage. Then you might have a voltage regulator circuit that maintains it at a constant 13.8 volts, which is the standard for mobile ham radio equipment, for example. So if you wanted to use a mobile ham radio in your ham shack, you'd get a DC regulated power supply, which would be made up, this is kind of a block diagram of 110 to 220 volts in, transform down, rectification, to pulsating DC, smoothed out DC, and then regulated DC finally out to your radio or whatever the load is. So diodes are the most basic kind of diodes, and there's a special kind of diode called the light emitting diode. Current through the diode in the forward direction, positive on the input side, cathode output side, will cause light to be emitted by a light emitting diode, and they come in various colors. LEDs have replaced lamps. Used to be you'd have indicator lamps on devices. Now LEDs are pretty much everywhere because they use a lot less power and they last a lot longer as well. That's a light-emitting diode, another semiconductor device. Transistors, we're not going to go heavy into this, you don't need to know it, but the name is derived from the term transfer resistor. And the basic characteristics of a transistor are that an input voltage or current to a transistor is used to control output voltage or current. And if a small signal at the input is amplified to a larger signal level, we say that the transistor is being used as an amplifier. Or we can say that a small signal at the input can turn on or off current at the output. Then we say the transistor is being used as a switch. So transistors are typically used either as amplifiers or as switches. And bipolar transistors were the first kinds of transistors made up of 3 layers of semiconductor material: positive material, negative material, positive material. This is a PNP transistor. Or the opposite, negative material, positive material, negative material. This is an NPN transistor. And a 3-legged bipolar transistor has a base, emitter, and collector pins. That's what they're called. And they can be configured in various different ways. And transistors look like this, or can be actually made much smaller now with surface mount technology. Transistors in a schematic are something like this. Here's a bipolar transistor with a base, collector, and emitter. The output is being taken from the collector here, and the input is coming on the base. So here we have a small AC signal coming in, being passed through a capacitor, because capacitors will pass AC, going to the transistor where it's amplified, being sent out again through another capacitor at a much higher output level. And so this is a transistor being used as an amplifier. These devices right here, those are resistors. We looked at those before. Here's our battery as well. So we've seen those schematic symbols. Field effect transistors are another kind of transistors. They use also the N and P type materials, and they don't have a base, collector, and emitter, though they have a source, gate, and a drain. And so here we have an N channel, a field effect transistor. The arrow points toward the N material. Or here is a P channel. More information than you need to know. Just know that field effect transistors are used in radios and other circuits for the same purposes that the bipolar, for amplification and for switching. And here is a field effect transistor in a circuit here. It's actually, in this case, being used as a switch. An input pulse comes in, and it controls an output pulse going out. That's more than enough information that you need to know.
Hey, Gary.
Yes, go ahead.
I remember this one, that a field usually has a gate to.
Yes, a field effect transistor has a gate input. Here's the gate, or back here, here's the gate. Usually the gate is the input, and it actually controls flow between the drain and the source. There's a lot more that I can tell you about it, but we don't have time, nor do we have test questions on that. But in the general class and the extra, we'll cover a lot more about it. Finally, integrated circuits, they have a lot of transistors and diodes and other devices built into them. Large-scale integration. That's all we need to know about integrated circuits. All right. Remember those formulas I showed you on the board with reactance, with capacitive reactance being inversely proportional to frequency, and inductive reactance being directly proportional to frequency? That comes into play in a special case called resonance, or resonant circuits. And it's an interesting thing that when the reactance value in ohms of the inductor equals the reactance value of the capacitor, a special dance occurs where the energy that's stored in the magnetic field of the inductor gets transferred to the capacitor. And the energy that's stored in the electric field of the capacitor gets stored back to the inductor. And this dance of energy going back and forth is called resonance. It can be a series resonance circuit like this, or it can be a parallel resonance circuit like this. And when that happens, in this very special case, this actually becomes at that one particular resonant frequency. Remember the formulas, the F, where the reactances are equal, this becomes a short circuit. And that frequency is allowed to pass completely unimpeded. That's a series resonant circuit. Whereas a parallel resonant circuit, where this dance of energy that's going on, this becomes a completely open circuit at resonance. And that is the principle of tuned circuits, which is, the only way that we can, tune our radio is by using the principle of resonance. And here's a pictorial of the energy swap that is going on, in this case, in a parallel resonant circuit. The field builds up in the inductor on the left, and then it's transferred back to the capacitor on the right. And if it weren't for circuit resistances, the resistance of the wire or whatnot, this, at that particular frequency, once it was energized, would go on forever. But because there are resistances, then power is lost. But if you keep pushing energy to this, then it will stay resonant. And this is how we get output circuits in transmitters that tune for a particular frequency. Just know that this principle of resonance exists. And impedance, we talked about it earlier, is measured the combination of resistance, normally on this horizontal axis, and reactance, normally on the vertical axis, and the magnitude. This is the impedance. You don't need to know a lot about it here in the technician class. Just know that it exists. So here's a review. Resistance, yes, measured in ohms with resistors. Yep, blocks resist the flow of DC current. Yep, okay. Capacitive reactance, measured in ohms, inversely proportional to frequency. Inductive reactance, measured in ohms, directly proportional to frequency. And impedance, the combination of resistance and a reactance, also measured in ohms. Okay. And resistance is the opposition of flow to a DC current flow. Impedance is the opposition to AC current flow. I know there's a lot, and we've kind of duplicated some stuff here, but let's see if it makes sense if we answer some questions. So what describes the ability to store energy in an electric field?
Capacitance? D?
Yes, capacitance stores energy in an electric field. That is correct. And what is the unit of capacitance?
Farad?
The farad is correct. You see, you know this stuff. And what describes the ability to store energy in a magnetic field?
Inductance.
Inductance, D. That's correct. And what is the unit of inductance?
Charlie.
Yep. The Henry, Charlie. The Henry is the unit of inductance. And what is the unit of impedance?
Delta.
You're going to have 4 ohm or 8 ohm speakers. Yeah. Ohm. Yeah. And what is impedance?
Alpha.
By definition, it's the opposition to AC current flow. And what electrical component opposes the flow of current in a DC circuit?
B, resistor.
Resistor. By definition, we said the resistor opposes current in a DC circuit. And what type of component is often used as an adjustable volume control?
Charlie.
Charlie, the potentiometer, variable resistor. And what electrical parameter is controlled by a potentiometer?
Resistance?
The
D?
resistance, yes indeed, it's a variable resistor. And what electrical component stores energy in an electric field? We had this earlier.
B.
B, the capacitor stores energy in an electric field. This is, they duplicated the question, but that's okay. And what type of electrical component consists of conductive surfaces separated by an insulator? Two plates?
D.
Did I hear B or D?
Delta.
Delta, yes, a capacitor. That's a capacitor. All right, and what type of electrical component stores energy in a magnetic field?
Charlie?
Charlie, the inductor, that coil of wire is making a magnetic field. And what electrical component is typically constructed as a coil of wire?
D.
Yeah, the inductor. And what is the function of a single pole double throw switch?
D, Charlie.
Charlie.
It's a single circuit being switched between one of two other circuits, yes. And what electrical component is used to protect other circuit components from current overloads?
Alpha.
That's a fuse.
Fuse. Yeah.
All right, let's take a look here at this pictorial. What type of switch is represented by component number 3? There's number 3.
That's a single pole, single throw alpha.
Alpha, single pole, single throw, the most basic kind of switch. And which is true about forward voltage drop in a diode?
Alpha.
Yeah, I showed you the germanium and the silicon diodes. Germanium is lower than silicon, so it's 0.2 versus 0.7. It's lower in some diode types than others. So what electronic component allows current to flow in only one direction?
Diode.
Diode, C is correct. And which of these components can be used as an electronic switch?
Charlie?
Charlie, the transistor. And which of the following components can consist of 3 regions of semiconductor material? NPN or PNP?
Ryan.
Resistor.
That's the transistor.
Bravo.
Yeah, triode is a kind of a vacuum tube. We're not going to learn about vacuum tubes, but transistor. And what type of transistor has a gate, drain, and a source?
Bravo.
That's the field effect transistor. And how is the cathode lead of a semiconductor diode often marked on the package?
B with a stripe.
With a stripe. And what causes a light-emitting diode to emit light?
Alpha.
Current flowing through it in the forward direction, and we call that forward current. And what does the abbreviation FET stand for?
Alpha.
No,
Delta.
Delta.
it is
Field
delta,
effect.
field effect transistor. And what are the names for the electrodes of a diode?
C,
Yep.
anode.
Anode and cathode, yeah. And which of the following can provide power gain or gain?
Transistor.
Transistors can be used as amplifiers, so they have gain. And what is the term that describes a device's ability to amplify a signal? Oh, we just defined it. I just gave you the answer. It's gain. That's a device's ability to amplify. All right. So what are the names of the electrodes of a bipolar junction transistor, the old style? They've got 3 leads: Bravo, the emitter, the base, and the collector. And what is the name of an electrical wiring diagram that uses standard component symbols? I mentioned it briefly. Schematic diagrams. All right, here's a schematic diagram. What is component number 1 in this figure?
Alpha resistor.
That is a resistor, indeed. And what is component number 2?
Transistor.
Transistor, that's B, yeah. And what is component number 3?
The lamp.
It is a lamp, indeed, very good.
That was a guess.
It almost looks like an LED, but it's a lamp. And what is component
Right.
4?
The battery.
That is a battery, that is correct. All right, another diagram, component number 6. What is 6?
Resistor.
Capacitor?
2 plates separated by an insulator, that is a capacitor.
Yeah.
That's the schematic symbol for a capacitor. Okay, and what is component 8?
A regulator?
No,
LED.
I heard it, yeah, LED, that is a diode that is emitting light. That's what those arrows pointing out here, that's light coming off of the diode, so that's a light emitting diode.
Hey, Gary,
Yeah,
you might contrast 5 versus 8 with the arrows.
sure, so here's a regular conventional diode right here, and here is a light emitting diode right here. And to complete the trifecta, this is what is known as a regulator diode or a Zener diode, which we haven't talked about at all, but those are all different types of diodes. All right, component number 9.
It's some type of resistor.
Variable resistor.
It's a variable resistor, a potentiometer variable resistor, yeah. And component number 4.
The movie comes out this Friday.
Transformer.
Yeah. Okay. Transformer, more than meets the eye.
That's the animated version.
That's it. All right. Okay. What is component 3? And you have to put on your thinking cap about this one. Here's 3.
That's a variable inducer.
Well, inductor. Yeah, you got the right idea. Yeah, variable inductor. It's an inductor, but with a tap on it that you can move to vary its inductance. So that's a variable inductor. Good job. All right, and in this figure, component number 4.
Antenna.
That is an antenna. Very good. So which of the following is accurately represented in electrical schematics? Think about this.
Charlie.
Yeah, how things are connected together, component connections. That's what schematics are all about. They don't tell you about wire links or how the components look. All right, which of the following devices or circuits changes an alternating current into a varying direct current? It's built of diodes. You might know.
Transformer, but
No, it is, you might.
Rectifier.
I didn't mention it specifically, but I hoped it was in your reading. A rectifier. A rectifier is something that changes AC to pulsating DC. And it's made up of diodes, a rectifier circuit. So what is a relay?
A.
It is an electrically controlled switch. Perfect. And which of the following displays an electrical quantity as a numeric value?
C.
Meter.
That's a meter. And what component changes 120 volts AC to a lower AC voltage for other uses?
B. the transformer.
That's a transformer, yeah. And which of the following is commonly used as a visual indicator? Is it on?
LED.
Is it off? Yeah, an LED. And which of the following is combined with an inductor to make a resonant circuit?
Capacitor.
It's, yes, a capacitor. You have an inductor and a capacitor, and they're doing that dance. They're changing energy back and forth at a specific frequency, and magic happens. Resonance. So what is the name of a device that combines several semiconductors and other components into one package?
Integrated circuit.
That's an IC, integrated circuit. Oh, more diagrams. What is the function of component 2 in this figure?
C, switch.
It's being used as a switch to control the flow of current. Perfect. And which of the following is a resonant or tuned circuit?
A.
You have to have an inductor and a capacitor, and they can be in series or in parallel. And what is the purpose of a fuse?
D.
No, it doesn't limit current. And it does not prevent power supply ripples. So it's to remove power. It doesn't limit current to a certain value. It just removes power completely in case of an overload. So why should a 5 amp fuse never be replaced with a 20 amp fuse?
To prevent smoke from coming out.
Yeah, excessive current could cause a fire, and you'll let the smoke out. Very good. All right. Briefly on some radio circuits here, last section. An oscillator, what I like to think of an oscillator, you've all been to a high school basketball game, and they've got the PA system, and they turn up the PA system too loud, and it starts howling and making a noise. I'm going to go ahead and mute everyone here just for a second. Reduce some background noise. Okay, good. That feedback that you have in the auditorium or in the gymnasium, that's an oscillation. And an oscillator is an amplifier, so the PA amplifier in the gym, and a feedback circuit from the speakers to the microphone, for example, in the gymnasium. Well, you can do it on a printed circuit board or in a chassis, and you can create something that will generate an AC signal electronically. It generates an output. And so an oscillator creates an alternating current output signal, and an oscillator is designed generally to put a signal out on just one frequency. So here we have a transistor that's being used as an amplifier, and we have feedback energy coming from the output side here on the emitter, going through some capacitors and being filtered by this crystal over here. So this is a crystal controlled oscillator, and so it's going to have an output on one frequency. And so filters are used sometimes after these oscillators just to remove any extraneous noise or other signals. You can have high-pass filters, low-pass filters, band-pass filters. There used to be a lot more questions on filters. There are no questions on filters anymore, but just be aware that they do exist, and they're used in all sorts of different circuits from radio frequencies to audio. A high-pass circuit here having a capacitor in series. Remember the capacitor's reactance varies inversely with frequency. So its reactance goes down as the frequency goes up, so it passes higher frequencies better than it does lower frequencies. So here's a simple high-pass filter, and these are the displays of amplitude versus frequency for a low-pass filter or a high-pass filter. Things to know, just to be aware of. There's always URLs down at the bottom of the slide that you can go to if you'd like to find out more information about the subject. Transmitters, well, that's what we're all about. We want to be able to transmit radio frequency signals. Here's a basic Morse code transmitter with an oscillator generating an AC signal, a driver amplifier, probably transistorized, Morse code key that is controlling both it and the power amplifier. Sometimes it'll only control one. And then an output power amplifier going to an antenna. So here's a block diagram of a simple Morse code transmitter. when you're sending Morse code, you're adding information to the radio frequency signal. And by adding information, we call that modulation. And you can have just on and off of Morse code, that's one kind of modulation. Or you can have audio modulation using amplitude modulation, which you see here, the amplitude of the radio frequency carrier is being changed in time with the audio, the modulation signal here, the voice. Or you can have frequency modulation down here where the amplitude is staying the same, but its frequency is varying in time with the audio modulation. So modulation in general is adding information to a radio frequency carrier, and here we have two different types, amplitude modulation and frequency modulation. And here's a block diagram of an old AM transmitter. This is like the old Gates transmitters I used to work on years ago. A master oscillator generating the frequency you're supposed to be operating on. A driver buffer amplifier going to a amplitude modulated power supply, and a very beefy audio amplifier that's supplying power to the output stage. And then you're broadcasting on the AM broadcast band. So here's an AM transmitter block diagram. All right, there's transmitters. Receivers, here's an old oldie but a goodie, an old communications receiver from Lafayette Radio Electronics. Super heterodyne receivers were the most common type in the past. They're being superseded by software-defined radios, which we won't go into. But you need to know about super heterodyne receivers is they use something called a mixer. In fact, I think it's right here on this block diagram. See here the mixer stage? So here we have an antenna for receiving. The signal is coming in. Oh, here's our friend the oscillator, generating, this was known as the local oscillator, a signal to go into the mixer stage. And what the mixer does is it takes these two signals, the input from the radio frequency and the signal from the local oscillator, and it changes the output frequency. Actually, on the output, you have the sum of frequencies, and you have the difference between the frequencies. This sum or difference is used, it's filtered with a filter and taken through an intermediate frequency stage. So the mixer actually will pass the input frequency, the local oscillator frequency, the sum and the difference. Whoops, went too fast. All four of those are passed, but filters come into play, and you either want the sum or the difference, one or the other, and that is passed into intermediate frequency amplifiers. So here's another block diagram, RF coming in, it's amplified. Here's our mixer with our local oscillator going down to an IF frequency, 10.7 megahertz for FM radios, for example, is the typical IF. And then it is demodulated. The information is gathered out of it and then goes to an audio amplifier to listen to. Those are very simplified pictorials and block diagrams of transmitters and receivers. All right, some questions here. Which of the following is used to convert a signal from one frequency to another in a radio?
Mixer.
That's the mixer. You have the input signal, you have the local oscillator signal, you have the sum or the difference, and that's used. All right? And what is the name of a circuit that generates a signal at a specific frequency?
Oscillator.
That's an oscillator. And which of the following describes combining speech with an RF carrier?
That's a modulator.
Yes, or modulation. That's, you're adding information to the carrier. And that, ladies and gentlemen, is the end of chapter 3, which I think is the hardest chapter in the book. So pat yourselves on the back. You've done great. Are there any last-minute questions before we go tonight?
I just want to say you took like a year of electronics and did it in 2 hours, so I feel bad for anybody who doesn't already know.
If your head is not exploding by now, it's not normal. So, but yeah, we covered a lot of stuff in a short period of time. All right, then I will wish you best regards in
Thank you.
Hamspeak 73, and we'll see you next week with Chapter 4. Come on back, y'all.
Thank you.